We're going to talk about polynomial functions. A monomial is a real number, a variable, or a product of a real number and one or more variables with whole number exponents. So for example, 3x to the fourth power, that is a monomial, that's one term. Also 3x to the fourth, y to the third, that would also be a monomial, it's still one term. The degree of a monomial in one variable is the exponent of the variable. So that 3x to the fourth power, the degree of that monomial would be 4 because the exponent is 4. A polynomial is a monomial or a sum of monomials. So that 3x to the fourth could be a polynomial, or you could have 3x to the fourth plus 5x to the third plus 6x squared. That's also a polynomial. The degree of a polynomial in one variable is the greatest degree, so the highest exponent among its monomial terms. So when you're talking about the degree of a polynomial in one variable, you're talking about the highest exponent among its terms. The standard form of a polynomial function arranges the terms by degree in descending numerical order. So simply put, what that means is decreasing order of the exponents. You start with the highest exponent and work your way down to no variable, no exponent, in other words, the constant term. That p of x equals 4x to the third plus 3x squared plus 5x minus 2, that is in standard form, decreasing order of the exponents. Now each of these terms has a name. That 4x to the third is called the cubic term because the exponent is 3. The exponent of 3 means cubic. Next up, 3x squared. We dealt with quadratic equations before. That is the quadratic term of that polynomial. The exponent is 2. Next, the 5x. It's called the linear term. We've dealt with linear equations where the highest exponent is 1. Well, that 5x has an exponent of 1. That is called the linear term. And finally, no variable, no exponent. It does not change. That's why it's called the constant term. So that negative 2 is the constant term of that polynomial. You can classify polynomials by degree or by its number of terms. So here we have a chart. Polynomial examples are in the middle. We're classifying by degree on the left and by the number of terms on the right. First up is 5. The number 5 is a constant term. The degree is 0. So the degree on a constant term is 0. By the number of terms, there's one term there. That 5 is just one term. That is a monomial. The prefix mono means 1. Next, x plus 4. By degree, the highest exponent is 1, so the degree is 1. That's called a linear polynomial because the degree is 1. And by the number of terms, there are 2 terms there, just like your bicycle has 2 wheels. This has 2 terms, so that's called a binomial. Next, 4x squared. By degree, the highest exponent, or the exponent, is 2. So by degree, that is a second degree polynomial, or in other words, a quadratic polynomial. By the number of terms, there's 1 term. That is called a monomial. Again, the prefix mono means 1. Next, 4x to the third minus 7x squared minus x. The highest exponent is 3. So that is a cubic polynomial, also known as third degree. There are 3 terms there, so with 3 terms, you've all ridden a tricycle before, hopefully not lately. With 3 terms, that is a trinomial. Prefix tri means 3. Next, 2x to the 4 plus 5x squared. To the fourth power, that is a quartic polynomial. The degree is 4, so the highest exponent is 4. And by the number of terms, there are 2 terms. Just like your bicycle has 2 wheels, that is called a binomial. And lastly, negative x to the fifth plus 4x squared plus 2x plus 1. By degree, you're looking at the highest exponent. The highest exponent is 5, so that'd be a 5th degree polynomial, also known as a quintic polynomial. There are 4 terms, and after 3 terms, after the trinomial, you can simply say a polynomial of 4 terms. That is how you classify a polynomial, by degree and also by the number of terms. Write each polynomial in standard form. What is the classification of each polynomial by degree and by the number of terms? So first thing we're going to do is get these in standard form. That is decreasing order of the exponents. So you start with the highest exponent, work your way down to no variable, no exponent, if there is that constant term. So 3x plus 9x squared plus 5. To get that in standard form, simply move that 9x squared out to the front. So put the highest exponent out to the front. It becomes 9x squared plus 3x plus 5. That is standard form, decreasing order of the exponents. To classify that by degree, look for the highest exponent. The highest exponent there is 2. So that'd be a second degree polynomial, also known as a quadratic polynomial. And to classify by the number of terms, there are 3 terms there. Just like your tricycle had 3 wheels, 3 terms would be a trinomial. Next up, 4x minus 6x squared plus x to the 4th plus 10x squared minus 12. To get that in standard form, we have 2 things to do. You need to combine the like terms, combine negative 6x squared with 10x squared. That would be 4x squared. And then also move that x to the 4th out to the front. So write this in decreasing order of the exponent. So combining the like terms, you get 4x squared. Move that x to the 4th out to the front. So it becomes x to the 4th plus 4x squared plus 4x minus 12. That is in standard form, decreasing order of the exponents. To classify that by degree, when you classify by degree, you look at the highest exponent. The highest exponent is 4. So that'd be a 4th degree polynomial, also known as a quartic polynomial. And to classify by the number of terms, count the number of terms. There are 4 terms there. Anything over 3 terms, anything over trinomial, you simply state that that's a polynomial of 4 terms. Which expression is a binomial? Binomial consists of 2 terms. Just like your bicycle has 2 wheels, you're looking for the one with just 2 terms. The one with just 2 terms is down here on the end, letter D, x minus 9. That is a binomial consisting of 2 terms. Next, what is the degree of the polynomial? 5x plus 4x squared plus 3x to the 3rd minus 5x. So when you're looking for the degree, you're looking for the highest exponent. The highest exponent of all these terms is this 3. So the degree on that polynomial is 3. What is the standard form of the polynomial? 9x squared plus 5x plus 27 plus 2x to the 3rd. To get that in standard form, you want to get that in decreasing order of the exponents. So start with the highest exponent. So you want to move that 2x to the 3rd out to the front. Then after that would be 9x squared, then 5x, and then the constant term, which is 27. So to get that in standard form, it'd be 2x to the 3rd plus 9x squared plus 5x plus 27. In this case, that's letter I. The degree of a polynomial function affects the shape of its graph and determines the maximum number of turning points or places where the graph changes direction. So turning points are places where the graph changes direction, but they are affected by the degree of that polynomial function, or the highest exponent on that polynomial function. It also affects the end behavior. So that degree, or that highest exponent of that polynomial function, affects the end behavior of the graph. That is directions of the graph to the far left and the far right. So end behavior, what's happening on the left side, what's happening on the right side of the graph, that's known as end behavior. A function is increasing when it moves upward from left to right. So as you scan a graph from left to right, as you read a graph from left to right, if the y values are going up, that function is considered increasing. A function is decreasing when it moves downward from left to right. So again, as you scan a graph from left to right, as you look at a graph from left to right, if the y values are going down, that function is considered decreasing. So if we have this graph here, y equals 4x to the 4th plus 6x to the 3rd minus x. The end behavior. What's happening on the left side? What's happening on the right side? Well, on the left side, it's going up, and on the right side, it's going up. So the end behavior, you could term as up and up. Turning points. Where is the graph turning direction? By turning direction, completely turning around and going the other way. One turning point, you can't see the coordinates, but I have them labeled for you, negative 1.07 and negative 1.04. Those are the coordinates of that turning point. And then it goes up and turns direction, starts heading the other way, so that is another turning point right there. Coordinates are negative 0.27 and 0.17. And then over here, it's going down and turns and starts going up again. So there is a turning point right there. Those coordinates are 0.22 and negative 0.15. So the function is decreasing when x is less than negative 1.07. So as you scan this from left to right, this function is decreasing right here when x is less than negative 1.07. Then the function is decreasing from negative 0.27, from x being negative 0.27 to x being 0.22. So where x is negative 0.27 to x being 0.22, that function is decreasing right there on that interval. Areas where the function is increasing would be right here, where x is negative 1.07 to where x is negative 0.27. That function is increasing when x is between negative 1.07 and negative 0.27. And then the function is increasing again over here to the right when x is greater than 0.22. So as you scan from left to right, the function is decreasing. The y values are going down right here, so the function is decreasing on this interval. Then it begins increasing, then decreasing, and then increasing again. You've seen graphs like this before. That is the graph of a quadratic equation. That is a parabola. It's the graph of y equals negative x squared plus 2x. As far as the end behavior goes, look on the left side, look on the right side. What does it look like on the left, and what does it look like on the right? So the graph looks down on the left and down on the right. So the end behavior you would state as down and down. For the turning points, there is just one turning point on a parabola. The coordinates of that turning point would be 1, 1. Now as far as the increasing and decreasing, read the graph from left to right. So as you read the graph from left to right, the y values are increasing up to that turning point of 1, 1, and then they start decreasing after that turning point of 1, 1. You want to use x as a measurement of what the y values are doing. So the y values are increasing where x is less than 1, and then the y values are decreasing where x is greater than 1. So to state the increasing or decreasing, the function is increasing when x is less than 1, and the function is decreasing when x is greater than 1. So again, the y values start increasing up to that turning point, and then they start decreasing after that. Next up, y equals x to the third. As far as the end behavior, look on the left, look on the right. What does the graph look like on the left? What does it look like on the right? Well, it looks down on the left and up on the right. So the end behavior is simply stated as down and up. As far as the turning points go, you got to be careful on this one. A turning point is when it completely turns and goes in the other direction, like this did back here. That is a turning point. But this continuously flows through. There is no change of direction. So there is no turning point. And then since there is no turning point, that means this function is consistently increasing for all values of x. So the function is increasing for all values of x. This is the graph of y equals negative x to the third plus 2x. To state the end behavior, you look at the left side, look at the right side. What's happening? What does it look like it's doing on the left? What does it look like it's doing on the right? Well, it looks up on the left and down on the right, so the end behavior you would state as up and down. As far as the turning points go, there are two turning points. Where it completely turns and goes in the other direction, that is a turning point. There are two of them. To get the coordinates on those turning points, you'd have to use a graphing calculator. The coordinates of this turning point would be negative 0.82 and negative 1.09. And the coordinates of this turning point would be 0.82 and 1.09. So the intervals of increasing or decreasing, there are three intervals here. From where x is negative infinity up to this turning point, and then from that turning point where x is negative 0.82 to where x is 0.82, that's the second interval. And then the third interval is from that turning point where x is 0.82 to where x is positive infinity. So the function, the y values are decreasing up to that first turning point. So you can say the function is decreasing when x is less than negative 0.82. The y values are decreasing where x is less than negative 0.82. And then the function starts increasing, but I also state the decreasing right here. The function is decreasing where x is greater than 0.82. So when the x values are greater than 0.82, the y values are decreasing. Now it only has one interval where it's increasing, and that is right here between those two turning points. So you can say the function is increasing when negative 0.82 is less than x, which is less than 0.82. So where x is between negative 0.82 and 0.82, the y values or the function is increasing. The end behavior, I got a little squeezed out there, hopefully you can still read it. The end behavior of a polynomial function with leading term ax to the n. So you can tell what the end behavior of the graph is based on that leading term, the coefficient of that leading term, and also the degree of that polynomial function. So if the coefficient, the a, the number in front of that leading term, if a is positive, if the leading coefficient is positive and the degree is even, then the end behavior would be up on the left and up on the right. If the leading coefficient is positive and the degree is odd, then the end behavior would be down on the left and up on the right. If the leading coefficient is negative and the degree is even, it's down on the left, down on the right. And if the leading coefficient is negative and the degree is odd, it's up on the left and down on the right. So here are some examples. Y equals 4x to the fourth plus 6x to the third minus x. So that leading term, 4x to the fourth, the leading coefficient is positive and the degree is even. So if the leading coefficient is positive and the degree is even, it should be up on the left and up on the right. It didn't lie, it is. Up on the left side and up on the right side. For y equals negative x squared plus 2x, look at that leading term. The leading coefficient is negative and the degree is even. So if the leading coefficient is negative and the degree is even, it would be down on the left and down on the right. As you can see, that is down on the left and down on the right. For y equals x to the third, the leading coefficient is positive, the degree is odd. So if the leading coefficient is positive and the degree is odd, it should be down on the left and up on the right, which it is. Down on the left side and up on the right side. Finally, for y equals negative x to the third plus 2x, the leading coefficient is negative, the degree is odd. So if the leading coefficient is negative and the degree is odd, the end behavior would be up on the left side and down on the right side. The chart doesn't lie. Just some other notes on polynomial functions. The graph of a polynomial function of degree n, where n is greater than or equal to 1, has at most n minus 1 turning points. So an example of that you can relate to is a quadratic function. A quadratic function, the degree is 2. It would have at most 2 minus 1 turning points, which it does. The graph of a quadratic function is a parabola. It has 1 turning point. The graph of a polynomial function of odd degree has an even number of turning points or none at all. So an odd degree function that you're familiar with is a linear function, a straight line, where the degree is 1. The graph of a polynomial function of odd degree or degree of 1, as in that case, has an even number of turning points or none at all. So that linear function that we're talking about, a straight line, would have no turning points at all. So once again, an odd degree polynomial function has an even number of turning points or it could have none at all. We had a y equals x to the third earlier where it had no turning points. The graph of a polynomial function of even degree has an odd number of turning points. So back to that quadratic function that you're familiar with, that is an even degree polynomial function, and it has an odd number of turning points. Consider each polynomial function. What is the end behavior of the graph? So we're going to start with y equals 4x to the third minus x. To state the end behavior, we need to know two things. What is the leading coefficient? Is it positive or negative? And what is the degree? Is it odd or even? So the degree here is odd. It's a third degree polynomial. The degree is 3. That's an odd number. The degree is odd, and the leading coefficient is 4. That leading coefficient is positive. So based on this chart, with the leading coefficient being positive and the degree being odd, the end behavior when I graph this should be down and up. Down on the left side and up on the right side, which it is. Next up, y equals negative 2x to the fourth plus 8x to the third minus 8x squared plus 2. It doesn't matter how many terms there are. What matters is this leading term. Is the leading coefficient positive or negative? And what's the degree? Is it odd or even? So the leading coefficient here you can see is negative. The degree is even. The highest exponent is even. So with the leading coefficient being negative, the degree being even, it should be down on the left and down on the right. As you can see here, it's down on the left side and down on the right side. Describe the graph including the end behavior, turning points, and increasing or decreasing intervals. We'll start with the end behavior. That's the easy one. What does the graph look like on the left side? What does it look like on the right side? Well, it looks down on the left and up on the right. So you'd state the end behavior as down and up. Now for the turning points, you got to be careful on this one. A turning point is when it completely reverses, goes in the other direction. So do the y values turn around and go in the other direction? No, they do not. There are no turning points here. And with there being no turning points, those y values, the function is always increasing from x being negative infinity to x being positive infinity. So as you read this graph from left to right, the y values are always increasing. So you could say the function is increasing from negative infinity to positive infinity. Now negative infinity to positive infinity, that represents the x values. The increasing, that's talking about the y values. Next up, y equals 3x minus x to the third. So first of all, the end behavior, the easy one. What does it look like on the left? What does it look like on the right? Well, on the left side, it looks up. and on the right side it looks down. So the end behavior is simply stated as up and down. Now for the turning points, you can see there are two turning points where those y values turn around and go in the other direction. And the coordinates of those two turning points, this left turning point would be -1, -2, and the right turning point would be +1, +2. And with there being two turning points, that creates three intervals. The first interval is from where x is -∞ to that first turning point. The second interval is from that first turning point to the second turning point. And the third interval is from that second turning point to where x is +∞. So you can say the function is decreasing to that first turning point. The y values are decreasing from x being -∞ to where x is -1. And then the the y values turn and start increasing. So you can say the function is increasing from x being -1 to x being +1. The function is increasing. And then after that turning point, the function starts decreasing. So the function is decreasing from x being 1 to x being +∞. So when you're stating that increasing or decreasing, you're reading the graph from left to right and judging what the y values are doing. From -∞ to 1 on the x-axis, the function, the y values are decreasing. And then from -1 to 1, reading that on the x-axis, from -1 to 1, the y values or the function is increasing. And then from x being 1 to x being +∞, the y values start decreasing.